Team 8, and this is our inverted pendulum robot. Process control is an inherent requirement for unstable processes, and is the very nature of an upright robot. Without any control, the robot would simply topple over. The aim of our project was to use a digital accelerometer and gyroscope in combination with an Arduino to keep our robot upright and self-balancing. When looking at the system transfer function, we can see that the system is naturally unstable, with not all poles lying in the open left-hand side of the complex plane. To combat this, we will introduce a restoring force through torque in the wheels. Instead of imagining the torque as accelerating the wheels back underneath the center of mass, we can instead think of the torque as applying a force on the center of mass to prevent the system from toppling under the force of the disturbance. To operate the amount of torque and stabilize the system, we introduced PD control. Looking at the transfer function, we can find through the final value theorem that the system will approach the set point under PD control. We can also derive the relationship for Kp and Kd by looking at this new transfer function. With this knowledge, we began building our prototype. Our chassis was designed in CAD to provide mounting for the motors, battery, and control board, and was then 3D printed. We selected the balance shield for Arduino as our sensor, as it comes equipped with a gyroscope, accelerometer, and a specialized library for control. We selected a 30-to-1 metal gear motor with encoder for its reversibility, high torque output, and ease of control with simple pulse width modulation.
Our code reads in data from the MP6050 IMU sensor into the Arduino microcontroller through I2C. Once the sampling rate is set, we can begin to read gyroscopic data used to determine our angles. Here we set the outputs to the L298H bridge that drives our motors forwards and backwards using pulse width modulation, and also sets our initial values for our PID controller. The loop here calculates the PWM output according to the input received from the motor encoders and IMU sensor. The balance control loop controls the direction of the left and right motors. If the PWM signal is less than 0 for the left and right motors, output 1 will power on and move the motors forward. Otherwise, output 2 will power on and move the motors backwards. If a large amount of disturbance is introduced and pushes the robot past the angle threshold of 45 degrees, the motor will power off to avoid unnecessary damage done to the body or the electronics.
Now let's test the disturbance rejection. And check the angle.
Go for it. It's like burning out.